Okay, this is the section 15.5 reaction spontaneity. The objectives today, we're going to differentiate between a spontaneous and a non-spontaneous process. We'll go over what those are in just a second. We'll talk about something called entropy and free energy, and how that relates to the spontaneity of chemical reactions and other processes. Um, Vaporization, remember, requires energy to change a liquid to a gas or a vapor. So we can go over all this vocab here, and the main idea is it's changes in enthalpy. Remember, that's the delta H we've had in the other sections. And entropy, which we're going to introduce here. Entropy is the symbol for it is delta S. Determine whether a process is spontaneous or not. Okay, so this is a definition of a spontaneous process is a physical or chemical change that once begun occurs without outside intervention. Okay, so many spontaneous processes require some energy from the surroundings to start the process. So that's if you wanted to light a piece of paper on fire, right? You'd have to put some friction on the match to get that started, and then use the flame from the match to get the paper on fire. But once you start the fire on the piece of paper, it's going to continue till that it runs out of paper or runs out of oxygen or something happens, right? It's not going to require any more input from you to keep going. That's a spontaneous process. Entropy is a measure of all the possible ways that energy of a system can be distributed, right? And it's kind of related to the number of particles and the ways they can be arranged. So this little graphic down here has the oxygen and helium on opposite sides of this little container with the valve closed here. If we open the valve, there's 4 different positions the oxygen and helium can be in. Oxygen can be on the left, helium on the right, helium on the left, oxygen on the right. They can both be on the left, they can both be on the right. So there's 4 different ways we can arrange those two things. Okay. Second law of thermodynamics states that the spontaneous processes always proceed in a way that increases the entropy of the universe. And the way I usually think of entropy is like this second bullet point here, that is considered a measure of disorder or randomness of the particles in the system. So the more disorderly, the more random the movements of the particles, the more entropy it has. Okay, the more spread out the particles are, the more disorder. So a gas has more entropy than a liquid or a solid. Okay, so that helps us with these changes of state, right? Entropy increases when a substance changes from a solid to a liquid, right? It's more spread out. Well, maybe not more spread out, but the liquid particles in liquid can occupy many more positions and be more random than they are in a solid, which has pretty much a fixed position. Go from a liquid to a gas, much more entropy in a gas, again, many more positions, much more spread out. Okay, so these two changes of state increase entropy. Uh, the opposite thing also decreases entropy. If we have condensation, gas going to a liquid, entropy is going to decrease. It's going to become more ordered. Liquid going to a solid, entropy is going to decrease. Okay, so these opposite, you have to know what increases it, but you also have to realize that the opposite things happen too, or it decrease the entropy. Dissolving a gas in a solvent always results in a decrease in the entropy. Okay, so that's because the gas particles are surrounded by the solvent and they don't have as much freedom of movement as they did before. Okay, usually if you have a chemical equation, right, and you have more um, molecules of a gas in the product side than you have in the reaction side, then that reaction had an increase of entropy, right? You have more gas in the product than you have in the reactants. Entropy always increases when a solid or a liquid dissolves in something, a solvent, usually water, right? Sugar or salt dissolved in water, those salt and sugar particles have much more randomness now. They're free to move about. The liquid, when it's dissolved in a solvent, it gets surrounded by the solvent and has much, instead of being surrounded by the liquid, its own stuff, it's surrounded by the solvent. So that liquid kind of gets broken up and distributed among the solvents. So it has much more randomness than 2. Randomness, entropy also increases as its temperature increases, and that's part of like the KMT, right? The kinetic molecular theory. The higher the temperature, the faster the particles are moving or vibrating, or so that makes sense that they'd have more entropy as the temperature went up. Entropy, we use delta S for that, and it's the S of the products minus the S of the reactants, okay? So you can predict the sign of delta S for the following phase changes. We go from a liquid to a gas, okay, or the products have more entropy than the reactants. Well, in this case, it's easy, right? Gases are much more random than liquids, so that's going to be a positive delta S. If we go from a liquid to a solid, okay, on the last slide we said what increased entropy. Well, this would decrease entropy, right? This would be solid, would be more ordered, there'd be less entropy after that was done. If a liquid was dissolved in some kind of solution, that's what AQ means. It's dissolved in water. So when you dissolve the liquid in water, that liquid has more positions than it had before. It's surrounded, all the liquid things are surrounded by the solvent, so there's more randomness to that liquid than there was before. If a gas dissolved in water, or that's what AQ means, is dissolved in water, that's going to have less entropy, right? It's going to be negative because the gas is free to move about, go spread far apart, and when they're dissolved, they are surrounded by the solvent and they can't move as freely as they did before. Okay, so some positive changes in entropy, delta S, right? That's how we usually change in entropy. I think of that as delta S. If the reaction or the process is exothermic, right? If it gives off heat to the surroundings, then it's usually that increases the entropy. Or if the process somehow of the system increases it just by like the change of state, right? That would be one thing for that second one. Okay. Free energy is the definition of free energy is energy that's available to do work, and we figured out with this formula. It's also known as the Gibbs free energy equation, right? We use delta G to figure out what that is, named after this scientist Gibbs who came up with this relationship. And it says that the delta H of the system, the enthalpy, okay, the heat given off or absorbed by the system, minus the temperature times the randomness of the system, the delta S of the system, is going to determine how much free energy we have, what the delta G is, the change in free energy. If this sign is positive, then the reaction is non-spontaneous, okay? It's not going to keep going on its own. You have to put some work into it to get it to go. If the reaction is negative, if the sign of delta G is negative, then it's a spontaneous reaction. Once you get it going, it'll keep going on its own. Okay, so the entropy of the universe always increases in any spontaneous process. That's a restatement of the second law of thermodynamics. And you have this little table here, and just the math behind this. If delta H is negative and delta S is positive, then when we do the subtraction here, we're always going to get a negative number. That's always going to be spontaneous. Have the opposite signs on those two, we're always going to get a positive answer, so that's never going to be spontaneous. If they're both negative or both positive, then it depends on the temperature, right? At lower temperatures, if they're both negative, then it's spontaneous at lower temperatures. If they're both positive, it's spontaneous at higher temperatures. Okay, so using the Gibbs free energy equation, sometimes you have, we'll just go through some easy ones like this, right? They give us the delta H and they give us the delta S. Is the process spontaneous at this particular temperature? Okay, so the first thing we have to do is that I have these two things circled because usually delta H is in kilojoules and delta S is in joules. So we need to get these two to be the same units in order to do this equation properly, right? So to convert the delta S to kilojoules. To do that, we need to take those joules and divide them by 1,000, right? There's 1 kilojoule has 1,000 joules. So we do that, we end up moving the decimal place over 3 places to be 0.322. Okay, so then we can plug these numbers into the equation. This is our delta S. This is our T in Kelvin. The T is always in Kelvin. And the delta H. Okay, so we do that math, plug it into your calculator, you get a positive 22 kilojoules. So is this spontaneous or non-spontaneous? Positive delta G means it's non-spontaneous. So this reaction will not go on its own, not keep going on its own. Okay, so the other times we ask the problems you have where it's what temperature would the reaction be spontaneous. Okay, so if we change the temperature on this system, what temperature would it finally be spontaneous at? Okay, so we have to figure out where this T, the temperature times the delta S, is greater than the delta G, delta H of the system. Okay, if that happens, then the delta G will be negative. Okay, so if this second term in the equation, this second term is bigger than this one, right? And it's, they're both the same sign, then that's going to create a situation where delta G is going to be negative. Okay, so we set this up, we plug in our delta S, we plug in our delta H, right? Solve for T by dividing both sides by 0.322. Okay, so then we get T, we do this math here, we get T has to be greater than 437 degrees. So after that, if we had that high a temperature, that would be a spontaneous reaction then at a temperature greater than 437. Okay, so here's some for you to practice. See if you can get this equation without so much help now, right? One of the things I will do, you have to watch the negative and positive signs, right? The temperature is always positive, right? Kelvin always has to be a positive temperature. But the delta H and the delta S can be positive or negative. So you have to be careful when you're doing this equation to keep the signs in there right. This negative is not the same as a subtraction, okay, on your calculator. So make sure you get that right. And another mistake students make a lot is a lot of times these delta S's are in the hundreds. So students get used to just putting the point, changing this to kilojoules by just putting the decimal point in front of whatever delta S is. And if that's in the hundreds, then that's fine, that works okay. But in this case, where it's only 55, if you put the decimal point in front of the 55, that's 0.552, which is not the same as what it should be. It should be 0.0552, right? This is correct with the extra decimal place there to get that delta S to have the right value in kilojoules. Okay, so you can test these out if you want, see how good you can work your calculator, see if you get the same answers I do. So you can pause the video right now if you want to try out your hand or not. So these are the answers you should have gotten when you do these problems, right? If it's negative, it's spontaneous. If it's positive, it's non-spontaneous. So try these out, right? Pause the video. You're going to have to do these, learn how to do these anyway. Make sure you know how to do them, okay? And a little review of vocab here. What's the measure of randomness in a system? Okay, so these two words, it's one of these two words. These two words are quite similar, right? So you got to figure out, they start the same and they end the same. So which one is it? All right. So that's the end of the video. I'll see you guys in class tomorrow.